Good afternoon, students. Once again, I welcome you all for this session. Okay. In the previous session, we have studied the procedure to be followed in the design of slab. So let us take one problem, okay, and try to design the slab. So the problem is like this: a hall has a clear dimension of 3 meter by 9 meter with wall thickness 230 mm. The live load on the slab is 3 kilonewton per meter square and a finishing load of 1 kilonewton per meter square. So that may be assumed. So using M20 grade concrete and Fe 415 grade steel, design the slab. Okay. So only the hall dimension is given and the live load and finishing load is given and grade of concrete and grade of steel is given. So for using this data, right, we have to design the slab. We don't know whether it is a one-way slab or two-way slab. Okay, so we are going to check first, then we are going to design according to the code. Okay, so now this is the hall dimension. So 3 meter. Now see, it is a clear dimension. It is not mentioned that effective. Okay, so 3 meter is a clear dimension, and again 9 meter is a clear dimension. So you can say that this is the shorter span. It is considered as LX, and this is the longer span. It is considered as LY. Okay, and this slab will be resting on two supports. Okay, whatever you are seeing this support, right? Each support will be 230 mm wide. Okay, so this room dimension is 3 meter by 9 meter. Okay. Now, as I told, this is the LX, okay, and this is LY. See, this is the cross section. So this is a slab. We have to find out what is the total depth of the slab and effective depth of the slab. And this LX is given. We have to take LX. Shorter span, you have to take for the design. That is LX. Right. So we don't know. What is the first step? First step is you have to find out whether this is a one-way slab or two-way slab. So for that, what we are going to take? We are going to take the ratio of Ly by Lx. Okay, longer span divided by shorter span. Then we are going to get the clear picture of whether it is a one-way slab or two-way slab. Now see, take a ratio of Ly by Lx. So now Ly is 9 meter and shorter span Lx is 3 meter. So what is the ratio now? Ly by Lx ratio? It is 3. So now what we say, code says, if the ratio Ly by Lx is greater than 2, okay, now this ratio is greater than 2, then this slab is designed as one-way slab. Okay, so if Ly by Lx ratio is greater than 2, then we are going to design the slab as one-way slab. And hope you already know what do you mean by one-way slab. So one-way slab is nothing but a slab in which it will going to bend only in one direction, that is along shorter span. So then you can say that it is a one-way slab. Now the next step, important step is the depth of slab, or you can say that thickness of slab we have to find out. So as it is a simply supported slab, it is not mentioned in the problem, but if nothing is given, you have to assume it is a simply supported one-way slab. Okay. Now for simply supported slab, as usual, span by depth ratio, that is effective span by effective depth, that is Lx by d. So remember, whatever may be the span, always you have to take the shorter span as the reference. So Lx by d. So into 20, as usual note, for a simply supported slab, the ratio will be 20, and for slab, when you are designing the slab, you have to multiply modification factor. It is nothing but, you can say that it is alpha. Okay, modification factor alpha. Okay, so or even you can say that it is a KT value. This modification factor is depending upon the KT value, right? So therefore effective depth is equal to what? Effective depth is equal to, that is d is equal to, right, Lx divided by this whole term, that is Lx divided by 20 into this modification factor 1.43 I have taken. How we have got this 1.43? So normally we assume how much percentage in the slab? 0.3 to 0.4% of main reinforcement we are going to assume. So for 0.3 to 0.4%, automatically this modification factor will be 1.43. Remember, so LH divided by this 20 into this value is 1.43. So calculate effective depth. So this effective depth comes out 112.93 mm. That is, effective thickness of this slab will be 112.93 mm. Okay. Now we have to assume the bar diameter, providing 8 mm diameter bars at clear cover of 15 mm. Okay. In the procedure also you have seen that. So for the main steel in the slab, you have to assume either 8 mm diameter or 10 mm diameter or maximum 12 mm diameter we have to assume. So let us assume 8 mm diameter for the main steel, and this steel will be placed at a clear cover of 15 mm. So in beam you have taken it as 20, but in slab, right, you have to take clear cover as 15 mm. So what is the effective cover now? Effective cover is equal to clear cover plus half the bar diameter. Okay, half the bar diameter. So that is 15. Clear cover will be the 15 plus bar diameter 8 mm means half of this will be 4. So effective cover will be 19 mm. So this effective cover is going to add to this effective depth. Therefore, we get overall depth of this slab capital D is equal to effective depth, that is small d, plus effective cover. So your overall depth capital D is equal to 112.93, that is small d, plus 19 mm effective cover. So overall depth is equal to 135 mm. Okay. Now what we are providing? So overall depth finally is 135 mm. So therefore effective depth D is equal to this overall depth 135 mm minus effective cover. So that is 135 minus 19. So finally we are providing the effective thickness or effective depth of this slab will be 116 mm. So final dimensions, these are the final dimensions. So effective depth is equal to 116 mm, right? Overall depth, that is capital D, is equal to 135 mm. And remember, this is the most important. So whenever you are going to design the slab, okay, the slab design will be for 1 meter strip. Remember, see here. So now see here, in this case, the slab will be put like this. Okay. So always you have to design 1 meter strip. So consider this is 1 meter strip. So whatever the design you are going to get, the same 1 meter strips you are going to provide for the other next strips. Okay. So this is a B now. Okay. So in slab, B will be 1 meter, and these are the other dimensions, that is effective depth, overall depth, capital B is equal to 1 meter strip, or it is 1000 mm. Okay. This is first step, you have to find out the dimensions. Next, second step is load calculation. So over the slab, load will be coming. So how much load we have to calculate? Again, as usual, right? First load you have to consider is dead load of the slab or self weight of the slab. How you have to calculate this? B into D, capital D, into density of RCC. So what is B now? 1 meter strip or 1000 mm. So you substitute here in meter. So 1 meter into capital D 0.135. Right? Then density of RCC is 25 kilonewton per meter cube. So dead load comes out 3.375 kilonewton per meter. Okay. Then second load, finishing load. It is given in the problem. Finishing load, it is 1 kilonewton per meter square. Okay. How much it is? 1 kilonewton per meter square. So multiply how much strip you are taking, you are designing B 1 meter. So 1 kilonewton per meter square into 1. So this comes out 1 kilonewton per meter only. Okay, this is second load, that is finishing load over the slab. So dead load, finishing load, and next is live load. Okay, the third load given, live load, it is 3 kilonewton per meter square. Okay, again it is multiply 1 meter width. So your total live load will be 3 kilonewton per meter. Then add all these three, dead load, okay, finishing load, and this live load. So if you add, you will get total working load, that is small w. Okay, working load W is equal to 7.375 kilonewton per meter. So for 1 meter wide strip, what is the total load? 7.35 kilonewton. So this will be in the form of UDL. Remember, this is in the form of UDL. So now this is working load, but we want factored load. WU we want. So multiply 1.5. So 1.5 into this W. So total factored load or ultimate load WU is equal to 11.062 kilonewton per meter. So this is the final ultimate load which is coming on the slab. Okay, so this is the second step. So the third step will be effective span of the slab. As usual, what you have followed the procedure in the beam, same steps will be there in this slab also. So the third step is effective span of the slab. Again, there are two criteria. Out of these two, which is the least value that will be considered as effective slab. So first criteria is effective span, that is L effective is equal to center to center of bearing. Okay, center to center of bearing means, so now again see here. So this is the cross section. So bearings are nothing but the supports. So from center of this support to the center of this support means it is an LX clear span plus half of this bearing plus half of this bearing, means one bearing we are going to add, that is clear span LX plus one bearing we are going to add. So clear span is 3 meter plus one bearing, that is 0.23 meter. So the total effective span is equal to 3.23 meters. This is one criteria. Second is effective span is equal to clear span plus effective depth. Okay, so clear span is 3 meter plus effective depth small d, what we have calculated, small d, it is 0.116. So this is 3.116. So out of these two, okay, out of these two, which is least value? This 3.116 will be the final effective span of the slab. So therefore effective span of the slab is 3.116 meter. Okay, so this is the third step. So the next step is, once we get the total load and effective span, then calculate bending moment and shear force for 1 meter wide strip of the slab. Okay, and as usual, you know maximum bending moment. Again, it is a simply supported slab. Okay, for simply supported slab subjected to UDL, the maximum bending moment will be at the center of this span, and it is given by WL square by 8. So maximum factored bending moment or ultimate moment is equal to WL square by 8. So W is the total factored load into L square. L is what? Effective span. Lx what we have calculated? Effective span, that L square divided by 8. So the maximum bending moment Mu is equal to 13.42 kilonewton meter. Okay, so this is the maximum bending moment. Similarly, what is maximum shear force or factored shear force Mu? Right? Again, for simply supported slab subjected to UDL, shear force will be, maximum shear force will be at the supports. Maximum shear force will be at the support, that is WL by 2. Okay, WU into L effective divided by 2. So substitute the values, then we will get the maximum shear force, that is Mu is equal to 16.593 kilonewton. So this is kilonewton and this is moment is kilonewton meter. This is the third step. Fourth step is what? Right? Next is you have to check whether the effective depth what you have calculated it is sufficient or no. For that, what we are going to do? Right? We will calculate the Mu limit. So next step is you have to calculate Mu limit. So depending upon the grade of steel, right? So you calculate Mu limit. So for Fe415 it is 0.138 FCK BD square. Right? So from that you can find out D required. Okay? So that D required, right? And what D we have provided, you have to check this. Okay, that is the next step. So once if you check is over, next is you have to find out the area of main steel, that is AST. Okay, so how we calculate the area of main steel? Right? So go to the procedure. Okay, so where we have already seen, right? Area of main steel. How to calculate the area of main steel? Then remaining procedure you can follow. So this is one video. The next part, the remaining steps, right? We're going to see in the second part of this video. Okay. So thank you very much for attending this session. Right. So in the next class we will continue with the other steps for this slab design. Okay. Thank you.